Hello class, I'm going to be talking today about Newton's second law for rotation. So you've already been exposed to Newton's second law for translation, F equals ma, and I'm now going to be teaching you the rotational analog of Newton's second law. So just off the bat, we know that some things have to be preserved. So on the regular Newton's second law, you have the sum of the forces equals mass times the acceleration. So you need to have a vector on the left side and a vector on the right side. So you need to have sum of something on here. Now for rotation, the analog of mass is the rotational inertia, I. And the analog for linear acceleration, A, is the angular acceleration, alpha. So we know that the right-hand side has to look something like this. Now if you look at the dimensions or the units of mass times acceleration, that's going to be kg meters per second squared. So that's what a Newton is. Newton is kg meters per second squared. Let's try to look at the units of the right hand side here. Moment of inertia is, the definition of the moment of inertia is sum of all the mi ri squared over all I, where the mass point mi is located at a distance ri from the axis of rotation. So the units of that work out to be just kg times meter squared. Alpha is measured in radians per second squared. So I have, the radians is not really a unit, it's the ratio of circumference to diameter of a circle, so we're not going to worry about that being a unit. But if you try to compare these two, you'll notice that it's a bit off. I have kg meters per second squared, meter squared really, so I'll write that as kg meters per second squared times meters, or newtons times meters. So the right hand side comes out to be newtons times meters instead of just newtons. So you can expect the left hand side also to have a quantity that has units of newtons times meters. And that quantity is what's called the torque, denoted by the Greek letter tau. And it's known as the torque. The proper definition of torque I will do in another video when I deal with cross products. But now let me just tell you how the torque is written. The torque is written as R cross F for a single force. So let me just give you the magnitude of this torque and the direction of this torque. So this is a special kind of product between two vectors known as a cross product. And there'll be a separate video about the cross products where you can learn about it in great detail. But right now, to set up Newton's second law, all I need to do is to tell you the magnitude and how to find the direction of this thing. So the magnitude of the torque, written just as tau without the arrow on top of it, is the magnitude of R times the magnitude of F times the sine of the angle between the two quantities, R and F. And the direction of this is given by what's called the right-hand rule. And this is how it works. If I think of this as my R vector and that as my F vector, then R cross F should be thought of as moving the R vector into the F vector using my right hand fingers. So if I use my right hand fingers, that's how the R vector will curl into the F vector, and the thumb points in the direction of R cross F. So that's called the right hand rule. So in terms of the right hand rule, we can write the direction n hat as given by the right hand rule. And the right hand rule is sometimes abbreviated as RHR for convenience. And that rule says if you curl the R vector into the F vector, with right hand fingers. Then the right thumb gives us the direction. Of R cross F, which in this case is just the torque. So the torque is out of the page, and you expect that to be the case because angular acceleration is either into the page or out of the page. So here you have an into the page or an out of the page vector. The left hand side must also therefore be an into the page or out of the page vector, so it all makes sense. The nature of the vectors should be the same on both sides. So now let's take a simple example of how to operate with this second law, and let's do it in a concrete problem situation. So I have here a massive pulley. So this is now a pulley that's got mass, and let's suppose it's uniform, and it's got some radius r, and I wrap around the pulley some string, and to the end of that string I attach some other mass. I'll call that mass little m. And now I would like to study how the system moves. The pulley is got an axle passing through it, so this part is fixed. If you want, I can draw the axle assembly with dotted lines here. So that part is fixed to the ceiling or someplace like that, so that cannot move. The pulley is only allowed to rotate, but this can go up or down. And let's just say initially nothing was happening, it was released from rest. So you expect this mass to eventually drag the pulley down. We'll assume the pulley is still ideal from the point of view of friction. There's no friction at the axle. So you expect this to start accelerating down with a linear acceleration A. And similarly, you expect the pulley itself to start accelerating, and I'll draw the angular acceleration alpha as this double shafted vector that's slightly curved to keep with our appearance of the double shafted arrow for linear acceleration. Now what we have to do is draw the free body diagram for each of these masses. So I'll do that right here. There's going to be the force of tension and the force of gravity, which is going to be greater than the force of tension because this wants to go down. So the force of gravity is mg there. And by Newton's third law, the equal and opposite force of tension will occur at the pulley level over there. Now, mind you, the r vector tells us how far the force is from the axle. That's what that r vector means. Okay, so in this case, r vector's magnitude is just capital R. The f vector is just ft, and sine theta is sine of the angle between the two, which is just 90 degrees. So that torque can be easily computed in this particular situation. And most problems, you'll find that the torque is easily computed using RF sine theta. And the sign convention I'm going to use for this particular case is the direction of torque is same as the direction of alpha. So in this case, if I take A to be down, alpha is going to be into the page. So the direction of torque is same as the direction of alpha. So I won't bother putting extra minus signs. I'll just take my direction of A to be the governing principle for the direction of alpha. So let's write the free body, let's write the equations corresponding to these free body diagrams. Let's do the torque one first. The sum of all the torques is equal to the moment of inertia of the pulley times alpha. Now, like I've already said, I'm not going to worry about the signs, so I'll just look at the magnitude. The magnitude of the torque is just going to be R times Ft times sine 90 degrees is equal to the moment of inertia of this pulley is a disk. So it's going to be 1/2 mr squared times alpha. So that's a great equation to have. Let's just save that. Let me write one more step before saving it. You'll notice that r and r squared cancel out there. So I get Ft equals 1/2 mr alpha. So I'll call that equation number 1. And this is business as usual. Sum of all the forces in the y direction equals mass times acceleration in the y direction. Well, that's going to give me mg minus the force of tension equals ma. So I have two equations now, an equation for ft and an equation for a, but there's also alpha. So this may be a situation with three unknowns but only two equations. But you remember there's a nice connection between translation and rotation, so we have to use that, the translation rotation connection. And this, in one of the previous videos last week, I showed you that this is this takes the form of A equals R alpha. So with these three equations, though, we can solve the problem completely. So I notice here immediately that R times alpha is in fact A. So what I'll do is I'll put equations 1 and 3 together to get Ft equals 1/2 ma, and then I can substitute 1/2 ma in there to solve the problem. So if I do that in equation 2, I get mg minus 1/2 capital Ma equals little ma. Capital M is the mass of the pulley and little m is the mass of this thing pulling it down, making it rotate. So now we'll solve for A by taking it on the other side. I get mg equals little m plus capital M divided by 2 times the acceleration, and this gives us the acceleration equals little m divided by little m plus capital M over 2 times g. And once you have the acceleration, you can also solve for the tension in the string. The tension F sub t from this expression is 1/2 ma, so it'll just be 1/2 little m times capital M divided by little m plus capital M over 2 times g. That's the tension in the thread. So in this manner, you can actually solve a lot of interesting problems. For example, any problem which has now got a pulley which is not a light pulley anymore, but it's a massive pulley, can be solved by this method of combining Newton's law for translation with Newton's law for rotation. This video is just an introduction to the subject. You should watch the subsequent videos to understand details of computing torque in other possible ways of doing the torque computation.